Okay, what if I told you our most powerful AI could run, say, 10 times faster, at just a fraction of the cost? Sounds pretty wild, right? Well, today we are diving into a huge breakthrough called ring linear that's about to do exactly that. Have you ever thought about this? Why can't we just feed an AI a 1,000-page report and get a summary back in like 2 seconds? Or have it scan a patient's entire medical history to find some super rare condition? The potential is obviously there, but there's a catch. And that catch, it's a massive computational wall. The thing is, when today's AI models try to process really long documents, they just grind to a halt. They get incredibly slow and super expensive to run. The very mechanism that makes them so smart is, ironically, their biggest bottleneck.
All right, so let's dig into this reading problem. Because to really get why this new stuff is so cool, we first have to meet the villain of our story. The technical bottleneck that's been holding AI back for a while now.
Okay, try to picture this. The standard AI's attention mechanism, it's like the world's most inefficient meeting. Seriously, for every single word, or token as they call it, to figure out how it relates to every other word, it basically has to have a private one-on-one chat. Now imagine a document with thousands of words. The longer it gets, the more one-on-one chats are needed, and the gridlock just explodes. It gets exponentially worse. So, at the heart of this whole mess are two competing ideas, two core technologies. On one hand, you've got something called softmax attention. This is the classic powerhouse, right? It's incredibly smart, super accurate, but it's the reason we have that horribly inefficient meeting. Then on the other hand, there's linear attention. This one's the challenger. It's super fast, really efficient, but on its own, it's always been a bit weaker, especially for those really complex tasks. So you're stuck with this classic trade-off. Do you want power or do you want speed?
And this chart, wow, it just lays the problem bare. That memory in AI needs to remember the conversation. It's called the KV cache. Well, with traditional softmax attention, it just explodes. The longer the text gets, the memory cost skyrockets. It goes vertical. But then look at linear attention. Its cost, totally flat. That right there, that's the bottleneck in action.
So, if one is powerful but slow and the other is fast but, a bit weaker, what do? Well, researchers came up with a brilliant solution, a new hybrid engine called ring linear, and it's an architecture that's designed to give us the best of both worlds. And that ring part of the name, by the way, that's a whole other cool thing. It's about this super efficient way data gets passed between the computer's processors, kind of like a baton in a relay race. It just helps minimize that gridlock even more.
And the core idea behind it is actually super simple and elegant. Think of it like a hybrid car, right? You use that ultra-efficient electric motor, that's our linear attention, for most of the driving, just cruising along. But you keep that powerful gas engine, our softmax attention, in reserve for when you really need it, like for a quick burst of acceleration to get on the highway. It's the same idea. Now, finding that perfect mix was absolutely crucial. It wasn't just a guess. The researchers ran a ton of tests, and they found the sweet spot, this optimal ratio. For their biggest, most powerful model, they landed on using 7 of the efficient linear attention layers for every 1 of the powerful softmax attention layers, just a 7-to-1 mix. And that seemingly simple change had massive, massive implications for both performance and cost. But okay, just mixing the two wasn't quite enough. To really make this hybrid engine sing, the researchers behind Ring Linear had to come up with 3 really specific critical innovations. This is kind of the secret sauce, right? This is what made the whole thing work so well. So here's the recipe for their success. First, like we just saw, they nailed that perfect hybrid ratio. Second, they didn't just use off-the-shelf stuff. They built their own custom, high-speed software tools to make the whole training process faster. And third, and this is a big one, they solved a really tricky problem by making sure the AI's training actually matched its real-world performance. Let's break those down a bit more, starting with those custom tools.
So for that second innovation, we're not talking about a small tweak here. They developed an entire software library, they called it linghe, filled with custom-built components. And get this, it sped up the entire training process by a whopping 50%. I mean, that's huge. Better tools, way better, faster results.
All right, now for that third innovation, and this one is genuinely fascinating. There's this deep-seated problem in AI called training-inference disparity. Here's the best analogy. It's like designing a race car in a simulator, but the simulator doesn't behave exactly like the real track. Even tiny differences between that training world and the real world can add up over time, and it causes the AI to become unstable and basically crash during training.
And here, this is what that crash actually looks like. This chart shows the model's performance, what they call its reward, during training, before they fix this problem. And you can see it's just all over the place. It's totally chaotic, completely unstable. This is a huge reason why training these big, powerful AI models can just completely fail.
But now, look at what happens after their systematic alignment. After they made the simulator match the real track. Just look at the difference. The reward curve is smooth, it's stable, and it's consistently rising. By solving this really fundamental problem, they could train their models for way longer and push them to a much higher level of performance. Okay, so they built a better engine. They stabilized the whole training process. So, what? What was the payoff? Well, now we get to the really exciting part, the results. This right here, this is the headline number. The Ring linear model gets top-tier performance at 1/10 the inference cost. And that's the cost of actually running the AI, not just training it. 1/10 the cost of a traditional model. That's not just a step forward. It's a massive leap in efficiency. And what about speed? Well, when it comes to that initial reading phase for a really long document, it's a process they call prefill. The new Ring linear model is more than 8 times faster than the baseline. It can just inhale huge amounts of information in a tiny fraction of the time. And believe it or not, the speedup gets even more dramatic when the AI is writing or generating a long response. Here, the Ring linear model is more than 10 times faster. 10! It's not just a little bit better, it is an entire order of magnitude more efficient. That's a game changer. So look, a 10-fold increase in efficiency is it's incredible. But what does that actually mean for us? Let's connect these technical stats back to the real world, to the impact this could have. And here's the most important part. They did not sacrifice smarts for speed. That's the key. The benchmark results showed these Ring linear models performed just as well, and sometimes even better, than their much more expensive competitors on really tough tasks, like complex reasoning, math, and coding. So you get faster, you get cheaper, and you get just as powerful. You get all three. And this is what that unlocks. We are now talking about AI that can finally tackle those huge context tasks we were dreaming about at the beginning. An AI that can actually read a patient's complete medical history. An AI that can analyze an entire code base for bugs. And because it lowers the cost so dramatically, this could truly democratize access to elite AI, letting smaller companies and research groups get in on the action. That computational wall, it's really starting to crumble. Which, of course, brings us to the final question. This technology removes a fundamental barrier. So now that we can give an AI a whole library's worth of information to process and do it efficiently and affordably, what's the first big, complicated problem we should ask it to solve? That's the new frontier this technology is opening up. Thanks for joining me on this one.